let's do an example. So we have a stressed out university student that drinks a Red Bull containing 500 milligrams of caffeine. He metabolizes caffeine such that every hour he reduces the amount of caffeine in his bloodstream by 10%. Okay, so what that means is that every hour, okay, we get a 10% reduction in the caffeine content, which means that we are left with 90%, right? Because if we reduce by 10%, that means that we have 90% left, okay? So every hour, we only have 0.9 or 9/10 of the initial caffeine that we had, right? Because it's a 10% reduction. Okay, and just for the sake of the problem, we're going to assume that all the caffeine that he consumes actually goes into his blood because we're talking about the concentration of caffeine in his blood. Anyway, to counteract the effects of caffeine metabolism, right? Because caffeine content over time is going to decrease. How fast specifically? 10% every hour, according to this problem. Not exactly true, but good enough for our purposes. And so just to counteract that effect, the student is smart, also stupid, but smart. He's going to take 10 milligrams of extra caffeine every hour. So on top of the initial caffeine that he took, which is slowly getting metabolized, he's going to add 10 milligrams of caffeine every hour to counteract those effects, okay, to slow down the overall metabolism. Because, well, not that it'll slow down the metabolism, but it'll just be more to metabolize. Anyway, so we're going to have CT, okay, the caffeine content at time t, represent the caffeine content in his blood after t hours. So that means that C naught is going to be the initial caffeine content, and we are told that that's 500, okay, 500 milligrams, and we're just going to use the caffeine content. We're going to say it's all in milligrams. And so what is the caffeine content an hour from now? Well, we know that it's a 10% reduction. So that's only 90% left. So 90%, we can also write it as 9/10. Okay, so an hour from now, we're going to have 9/10 of the caffeine we had before. Okay, that's our 10% reduction. But this guy consumes an extra 10 milligrams every hour. So we're going to add 10 milligrams here. Okay, because every hour, even though we lose 10% of what we had, we gain an extra 10 milligrams because the guy drinks it. Okay, so for part A, our dynamical system is going to be CT plus 1 is equal to 9/10 CT, right? This is the 10% reduction, okay, plus 10, which is the value that we're always introducing. And so if we wanted the updating function from that, just call this f of x, replace the CT by x, and we get 9/10 x plus 10 is our updating function. That is it, okay? This is our answer for part A. That's the updating function. Now for part B, by the way, based off this updating function, we can see that 9/10 is our R value and D is our 10, and D is 10. And so when we want to find the equilibrium, which is part B, all we have to do is remember that the equilibrium is for this kind of system, right? For the kind of system that is given by f of x is equal to Rx plus D, the equilibrium is x star is equal to D over 1 minus R. And D over 1 minus R is going to be 10 over 1 minus 9/10. So it's going to be 100 milligrams of caffeine. Not bad. Okay, that's the equilibrium. That's our X star. Now, if we didn't want to use this equation, how do we find the equilibrium? This is the general way it always works. The equilibrium condition is X star is equal to f of X star. Why is that? Because f of x is going to give, it's the updating function, right? So whatever we plug into there is going to give what it returns, what it equals to, it's what's next, right? So if I plug in, one value in here and I evaluate it, I'm going to get the next value that's going to come out. Now for an equilibrium, what you put in, if it's actually an equilibrium, if you take the updating function in the equilibrium, you're asking what's after the equilibrium. If you're already there, well, you're already at equilibrium. So what you get out of that is the equilibrium. So that's why solving this equation is going to give you the x that satisfies this, which is the equilibrium. So you want to solve this, great. And you will get x star is equal to f of x star. What's f of x star? 9/10 x star plus 10. Go ahead and solve that, move the x star to the other side. We get x star over 10 is equal to 10, so x star must be 100. That's not news. We just got that. Okay, that's our equilibrium. Now, next we want to calculate C10, C30, and C48. Okay, so we want to calculate C at time 10 hours in, C 20 hours in, and C 24 hours in. Sorry, C 30 hours in and 48 hours in. So how do we do that? Well, what you could do, right, is you know that C naught is 500, and you could just do, well, f of C naught is going to be C1, and then you can do f of C1 to get C2, and then you could do f of C2 to get C3, and you could do that all the way to 48. Or you could remember that we have an equation for it, right? When your system is of the form Rx plus D, if that's your updating function, if f of x is Rx plus D, then you know that your solution, your general solution, in this case is going to be CT. It's R to the T times x naught minus x star plus x star, okay? Now, in our case, x star is 100 milligrams and x naught is 500 milligrams. And so if we plug those values in, CT is going to be R. And what's R, by the way? Well, we already said R was 9 over 10. So it's 9 over 10. And when you're entering it on your calculator, be careful. It's the whole 9 over 10 that's to the T power. And we get x naught minus x star. What's x naught? It's 500. 500 minus 100 plus x star. What's x star? X star is 100. So our equation thereby becomes 9 over 10 t. 500 minus 100 is 400. All of this plus 100. And so if we go ahead and we plug in the values of t that we want, namely 10, 20, 30, and 48. So 10 hours in, right? This is the same equation. This is 9 over 10 t times 400 plus 100. 10 hours in, we're only going to have 249. So we do a pretty good job at getting rid of the caffeine. Then 30 hours in, we're going to have 116. So that's another good reduction. And 48 hours in, so if he keeps this habit up for 2 days straight, which is a lot, he's going to have 102 milligrams of caffeine in his blood, which is not a good amount to have chronically, but it's, as far as the guidelines go, apparently not enough to kill you. So that is it for the problem. Hopefully that helps.